2 times or fold was purified the enzyme just in one simple step of chromatography. And we do the same. We divide this specific activity by this to obtain the final fold of purification. The purification yield is a similar measure of the process of efficiency, but it actually measures how much of the protein activity remains after each step of purification. And this is expressed in percent. So obviously 100% for the lysate, because we haven't lost anything yet. Then we get the total activity from here and take the percentage of the total activity at each step. So we divide this by this and multiply by 100. And we get 83%. And then we do the same for the final step, divide this by this and multiply by 100, and we get 76%. So 76% of the protein remains of the enzyme remains in our final sample in terms of activity. Of course, it might be, in terms of protein, it might be different, because during the process of purification, the enzyme molecules might have experienced certain changes in their conformation and their activity, catalytic activity, which is expressed by Vmax and the turnover number, might have changed. We cannot know for sure because we don't have enough data to assess this. But based on specific activity and total activity, we can tell that about 76% of the activity remains. Okay, so this is how you do it quickly and easily, all those calculations by using a table, a simple algorithm that uses a table to calculate. And now we get to the second part of the problem, where you are asked to determine or estimate the molecular weight of your protein. To do this, we use a very useful relationship, which turns out to be linear, between the logarithm of the molecular weight. You can use base 10, or you can use any other logarithm. It doesn't really matter, but we usually use logarithm base 10, and the relative mobility of the protein. So how do we calculate the relative mobility if it's not given? I will briefly discuss it again. So this is our gel, and we have recall that when we prepared our sample, we mixed it with a sample buffer that had something blue in it. This blue has just one purpose. It's a dye that runs faster than any protein, and we just use it to determine when to stop the separation. When the blue dye reaches the bottom of the gel, somewhere here, we will disconnect the gel box from the power supply and then take out the gel and stain the protein. So this front of the blue dye is the distance relative to which we will determine the relative mobility, or the, as it's called, RF. And RF stands exactly for relative to the front. This is the front. Okay? So when we stain our gel, we will have this front, and we'll have also the ladder consisting of 10 different bands. And we will have our protein that migrated to a certain distance. So we take this distance to be the front, and then we will determine the RF of our protein by dividing this distance to this one. The RFs will be always less than 1 because the front is the longest distance. And then we calculate those RFs for all the bands of the ladder and plot them here in dimensions. So on the x-axis we will determine the relative mobility, and on the y-axis will be the logarithm, the log 10 of the molecular weight. So each data point will be determined by its RF and the log of molecular weight. And when we plot all the different proteins from the marker, they will arrange more or less along one straight line. Okay? So you then use a ruler and draw the line in such a way that it either goes through all the data points or you minimize the difference from each data point to the corresponding point on the line. This is the easiest and quickest way to do it. You can do some mathematics to calculate it in a more deterministic way, but it will waste time for you, so it's better to do it like that. So let's say on your graph paper your dots are something like that. You then take the ruler and draw the line in a way that will minimize your standard error. Okay? And this is your calibration curve. Then you take your data for the protein, the relative mobility, and find it on the x-axis. So we said it's 0.56 or something to come here. And we find the corresponding point on the calibration curve. So the corresponding point is here. And then we find the corresponding value on the x-axis. So it's 4.32 something. Okay? 4.32. And then 4.32, we know that 4.32 is actually the logarithm of our unknown molecular weight. And from this formula, it's very easy to calculate the molecular weight, because the molecular weight is simply 10 to the power of 4.32. So if you have